Welcome to day 9 of the Intuitive Calculus course. Today we're going to focus on the physical interpretation of the derivative. Let's review what we saw yesterday. We talked about the geometric interpretation of the derivative, and the conclusion we arrived to was that the derivative of a function f of x at point x0 is the slope of the tangent line at that point. That is, if you have the graph of a function like this one, and you fix a point on the graph, and you take the tangent line to the function at that point, then the derivative of the function at this point equals, by definition, the tangent line of this purple line here, this tangent line. And this is only a geometric concept, and what I want to do today is to give this concept a physical meaning. We're going to give a physical interpretation to this geometric concept. And to do that, we're going to begin with a very simple model that is used in physics. That is movement at a constant velocity. We're going to consider a train traveling at constant velocity, say 80 kilometers per hour. Here we have our train, and here we have an initial time that we're going to consider 0. Here we have a final time, and here we have some intermediate times. We're going to fill this table here. We're going to write down here the intermediate times, and on this column the distance covered by the train at each of those times. So for example, at the initial time 0, the distance is 0. After 2 hours, the distance is 160 kilometers, and so on. After 3.8 hours, you have this distance. After 6 hours, you have this distance, and so on. The final time is 10 hours. We calculate all these distances using the velocity. We know that the velocity is constant, and it equals 80 kilometers per hour. So we can calculate this distance by multiplying the velocity by the time and get distance. So we have this table here, and what we can do with a table is to plot the points. We can plot distance as a function of time. That is, we draw some axes. Here the horizontal axis will be time, and the vertical axis will be distance, and we plot these points. We get 6 points, and we can see that a curve that will fit these points is a straight line. So we draw these straight lines that goes through those points, and we know how to calculate the slope of this line. The slope is defined as delta y over delta x. But here let's remember that delta y is distance, because the vertical axis is for distance. So delta y is measuring distance, and in physics, distance, we use the letter s for distance. That's why here we change delta y for delta s. And on the x-axis we have time, so delta x, we can write delta x as delta t. So here we have distance over time, and that's how we measure velocity. For example, kilometers per hour, miles per hour. That is, velocity is distance over time, and this is average velocity. So when we're calculating the slope of this line, what we're calculating is average velocity. So this gives us an intuition that there should be at least some relationship between the derivative and the concept of velocity, because the derivative is a generalization of the concept of slope. And now, to view where is that relationship, we need to consider a more complex model. That is, we're going to say that the distance traveled by a car is represented by this graph, we're going to think again that on the horizontal axis we have time, and on the vertical axis we have distance, and the change in distance over time is represented by this graph. Here again we can calculate the average velocity between 2 points, for example these 2 points, by calculating delta x and delta y and taking the quotient between those. Doing that calculation, what we get is the average velocity between these 2 points. And now the question is, how do we calculate, for example, the velocity at this point? I don't want the average velocity, I want the velocity at this specific instant. For example, t equals 1. What is the velocity at this point? And what we can do is to try to approximate because we're in calculus, we know how to take limits, so we can make use of that. So we're going to approximate the velocity at this point by taking closer and closer average velocities. That is, we're going to make delta x smaller, even smaller, and we're going to take the limit as delta x approaches 0. And if we do that, well, we're going to define the speed at this point and this limit as this limit. This is how speed is defined in physics, as this limit. The limit as delta x approaches 0 of delta y over delta x. That is the limit of the average velocities. And in this case we don't have average velocity. This limit is instantaneous velocity, or more generally instantaneous rate of change, because velocity is the rate of change of distance over time. That's velocity. So more generally we can think about the derivative as instantaneous rate of change. That's a physical concept, and velocity is not the only concept that can be thought of as an instantaneous rate of change. For example, electric current is defined as the instantaneous rate of change of electric charge over time. So we use a derivative there to define electric charge also. And there are many other concepts in science that are defined like that, as rates of change. So that's the physical interpretation of derivative. That's all for now. Thank you for watching and see you next time.